talking about the scientific method in statistics class.
I have vague memories of hearing about the scientific method in high school science classes. It starts with defining a question and gathering information, then coming up with a research hypothesis, then testing the hypothesis by collecting data, analyzing the data, and then interpreting the data.
Oh, I bet that part about analyzing data involves statistics.
There's even a tool in statistics called hypothesis testing. It results in a statistical conclusion, and that allows us to evaluate the research hypothesis and come up with a research conclusion.
Wait, you mean there's like a parallel world? Like there's a research hypothesis and a research conclusion, as well as a statistical hypothesis and a statistical conclusion?
Yes, except that it's sort of like a statistical world is embedded inside of a research world.
Don't we just have one research hypothesis? It's weird because my professor talked about two statistical hypotheses, the null hypothesis and the alternative hypothesis. Null refers to nothing. So I guess the null hypothesis predicts that there will be no difference between the two conditions in the experiment.
That's the gist of it, but even more precisely, the null and alternative hypothesis are predictions about the parameters of the population. The statistical conclusion will be about those parameters. From there, you can evaluate your research hypothesis.
I don't really get that. What do parameters have to do with the conditions of my experiment?
Well, a null hypothesis usually says that two population parameters are equal. That's a quantitative way of saying that two groups are the same. The alternative hypothesis usually says that two parameters are not equal. The two groups are different.
That alternative hypothesis sounds like the research hypothesis.
Often that's the way it is. So if the data supports the alternative hypothesis, then it also supports the research hypothesis.
Oh, but that sounds sort of like we are accepting the alternative hypothesis. But I think we're not supposed to do that. We're simply supposed to reject the null.
Oh yeah, you're right about that. Do you know why though? I've always thought it just made things extra confusing.
Well, it helps to keep in mind that statistical inference is all based on probabilities rather than certainty. We reject the null when there is a very small probability that the null hypothesis is correct.
Oh, that's where that alpha comes in, right?
Yeah, the alpha is like the standard of improbability. We're asking ourselves, if it is very unlikely that the sample came from the null population, then we should reject this hypothetical population.
Oh, so that is why the alpha is usually a very small probability, like 0.05 or 0.01?
Exactly. So if there is less than a 5% chance that the sample came from the true null hypothesis, why would we assume that the null is true based on this sample? That would be foolish. We would reject the null.
Wait a sec. The null can be true, but we can reject it or fail to reject it? But also the alternative can be true, but we can reject it or fail to reject it? Sounds like I have to juggle a bunch of possibilities.
Yes, at the end of hypothesis testing, you can potentially be correct or incorrect. But you can be correct in one of two ways, or incorrect in one of two ways.
Let me see. At the end of hypothesis testing, you'll either reject the null hypothesis or fail to reject it. That we know for sure.
Right, we know our decision. But what we don't know is the actual state of the world. Either the null can actually be true, or it can be false.
So let's just say we decide to reject the null, if the null is true. Then we have just made a mistake. If the null is false, then we're correct.
I believe that kind of a mistake is called a false alarm, or a type 1 error. We decided there is a difference between two groups, but actually there isn't. It's like we decided to give surgery to someone who didn't actually have a tumor.
Well, let me try an example. A false alarm in an experiment might be saying that the weight loss drug worked when the weight loss drug didn't actually work. I think that makes sense. That would be a pretty serious error on the part of science. But what if we fail to reject the null? Can't we still be correct?
Yes, if we fail to reject the null when the null is false, that's a good thing. That's like saying that we don't want to perform surgery on someone who is perfectly healthy. Unfortunately, those kinds of studies tend not to be published.
Yeah, because that's like saying that a drug didn't work when it actually doesn't work. Usually people are less interested in finding out what does not work.
Yeah, I think that's also why type 2 errors, or misses, are also seen as less serious than type 1 errors. For instance, if we say that a drug didn't work, but it actually does work.
But I can think of situations where that is serious error too. I mean, what if we're just sitting on a drug that cures some big disease, but we rejected the null?
Absolutely. Type 2 errors are very serious as well. That's why you have to consider the ramifications of both type 1 and 2 errors when we're conducting experiments.
Wait then. What is this p-value? Does that have something to do with these type 1 and type 2 errors?
The p-value is the probability of getting a sample statistic as extreme or more extreme, given that the null hypothesis is true. So both the alpha and the p-value assume that the null is true.
And what's the difference?
Well, p-value depends on the sample. So in hypothesis testing, we start off by assuming that the null is true. We happen to get a particular sample. p-value is the likelihood of getting the sample or one that is even more extreme.
So that sample is highly likely to have been randomly drawn from the population and the p-value is very high, and if it's unlikely, the p-value is low.
You got the idea.
So I guess that's like saying that the p-value is a false alarm rate for a particular sample.
You can think of it like that. For instance, let's say we have a sample that has the p-value of 0.08. That's like saying that we have a probability of 8% of getting a sample that is this different or even more different from the null hypothesis, given that the null is true. It's a pretty small number.
But not smaller than 5%.
Right. Because it's not smaller than 5%, we're going to play it conservatively and fail to reject the null. We don't want to have an 8% chance of false alarm. We will only tolerate 5%.
But if the p-value is very small, like 1%, it's like saying that the chance of getting a sample or a more extreme one is smaller than our set tolerance for false alarms.
Which means you should accept the alternative hypothesis, that your sample comes from some other hypothetical population.
You mean reject the null hypothesis. We don't really say accept the alternative because our actual evidence just says that the sample is unlikely to have come from this null population. But that doesn't automatically mean that it is unlikely to come from some other population.
Right.
You know, this helps because I can never remember whether the p-value should be smaller than or greater than 0.05. I realize now that I can just reason it out. It helps knowing what this alpha equals 5% stands for.
And it helps knowing what p-value means too.